Look at this photograph of a patient in intensive care. For months, they've survived entirely on mathematically precise intravenous nutrition, known as TPN. Then, out of nowhere, a bizarre clinical cascade begins. Their proximal muscles severely weaken. Their heart dangerously dilates, struggling to pump, and their thyroid hormone profile becomes entirely chaotic. Confronted with this, the standard medical instinct is to hunt for a massive pathology, an aggressive viral infection destroying the myocardium, or perhaps a rare pituitary tumor short-circuiting the endocrine system. But the actual culprit is completely invisible to a standard metabolic panel. The patient is suffering from the total systemic absence of a single non-metal trace element, selenium. This creates an absolute clinical paradox. While the patient actively crashes from this deficiency, the hospital's mass spectrometer might report a falsely reassuring, completely normal selenium level. Solving this fatal contradiction requires us to trace the element's path, from the ICU bedside down to the molecular physics operating inside that mass spectrometer. Long before complex life existed, ancient single-celled organisms thrived in an environment with almost zero oxygen. They relied on selenium's extreme chemical volatility to catalyze their basic metabolic reactions. When the Great Oxidation Event flooded the atmosphere, breathing oxygen became a biological necessity, but it also generated highly unstable byproducts. In this simulation, you can see how unchecked oxygen-free radicals violently dissolve a cellular membrane. Rather than abandoning its ancient metabolic machinery, multicellular life repurposed it. The volatile selenium system became an active, microscopic shield built specifically to neutralize the toxic exhaust of aerobic respiration. To achieve this, the human body routinely breaks its own rules of genetic translation. It goes to extreme lengths to physically weave this volatile element directly into the primary support beams of specific cellular proteins. In these proteins, selenium is woven into the primary peptide backbone, functioning as a genetically engineered redox shield that prevents human tissues from rusting away from the inside out. When your cells manufacture standard proteins, they use reliable, stable amino acids, like native cysteine, as the structural bricks. But for 25 highly specialized human proteins, the cell makes an exception. It replaces a native sulfur atom with a selenium atom, creating selenocysteine, classified by biochemists as the 21st amino acid. This diagram illustrates the physical chemistry of that substitution. By swapping in selenium, the molecule's pKa drops from 8.3 down to 5.2. While standard cysteine holds onto its proton and stays neutral, the selenocysteine instantly ejects its proton and becomes fully ionized. Because our blood maintains a pH of 7.4, that low pKa ensures the selenium core stays permanently ionized. It operates as a microscopic lightning rod, transferring electrons at incredible speeds to neutralize localized oxidative fires. Installing that lightning rod requires a massive genetic gamble. The cellular machinery must read the UGA triplet in the messenger RNA, a sequence universally recognized as the strict, unambiguous stop codon for translation. To bypass this stop sign, the messenger RNA strand utilizes a specialized three-dimensional fold called the secus element. Sitting just downstream, it physically recruits proteins that force the ribosome to ignore the termination signal and insert the volatile selenium core instead. This molecular architecture also regulates the endocrine system through a family of proteins called the iodothyronine deiodinases. Your thyroid gland continuously produces thyroxine, or T4, but T4 is entirely inert. The deiodinase enzyme uses its highly reactive selenocysteine core to physically rip an outer ring iodine atom right off the T4 molecule. That single atomic subtraction is the exact mechanical trigger that converts the inert T4 into the highly active T3 hormone, which then enters your cells and fires up your systemic metabolic rate. Without this atom, the thyroid gland pumps out T4 perfectly, but the body lacks the chemical power to activate the hormone, causing the systemic metabolic rate to collapse. Despite dictating both antioxidant survival and metabolic output, your entire systemic inventory of selenium is astonishingly small, amounting to just 15 to 20 milligrams, mostly sequestered nonspecifically in your skeletal muscle. Because human biology cannot synthesize this element from scratch, our structural integrity is completely dependent on the concentration of selenium in the soil where our food is grown. Look at this source image. Depending on the local soil profile, a single Brazil nut can pull up to 100 micrograms of raw selenium from the dirt, making it the most concentrated dietary source on the planet. Once ingested, your liver acts as the central processing plant. It extracts the raw dietary selenium and synthesizes an extracellular transport truck called Selenoprotein P, capable of carrying up to 10 selenium atoms per molecule. Under steady conditions, this transport network runs flawlessly. But during severe trauma or septic shock, the architecture undergoes an acute collapse. Massive systemic inflammation signals the liver to immediately halt the production of selenoprotein P. Simultaneously, capillary leak syndrome forces the blood vessels to become highly permeable, draining the existing transport proteins right out of the vascular space. Within 24 to 48 hours of critical illness, the delivery network completely fails. The tissues are starved of their primary redox shield exactly when the body is fighting maximal oxidative stress. We can observe the consequences of a chronic delivery failure in populations living on severely depleted soils, which drives an endemic deficiency known as Keshan disease. Lacking the raw atomic materials to build their glutathione peroxidase enzymes, these patients' heart muscles are left entirely defenseless against the oxidative stress generated by every single heartbeat. This diagram illustrates the resulting host-pathogen interaction. Without the selenium shield, unmitigated free radicals flood the cell. If a common, normally benign enterovirus enters this environment, the free radicals physically damage its RNA polymerase. The host's nutritional deficiency actively forces the virus to make copying errors. It rapidly mutates into a lethal, highly virulent strain that shreds the heart muscle. The opposite extreme is equally destructive. Chronic selenosis occurs when massive oversupplementation or highly seleniferous soils flood the body with excess trace metal. The cellular machinery struggles to distinguish between a native sulfate atom and an excess selenium atom. It begins erroneously inserting the metal directly into structural keratin proteins. This single atomic mistake warps the internal geometry of the tissue. Crucial disulfide bonds destabilize, causing patients to experience progressive patchy hair loss, severe neurotoxicity, and structural nail shedding. To vent these acute toxic overloads, the liver engages a specialized emergency valve. It converts the raw excess into highly volatile dimethylselenide gas, physically exhaling it through the lungs and producing a pathognomonic, intense garlic breath odor. From the weaponization of benign viruses to the physical uncoiling of structural proteins, these extremes prove that human survival requires an incredibly tight, highly regulated homeostatic balance. To track that balance, clinical laboratories face a monumental task, accurately measuring a few micrograms of a highly volatile element while navigating a dense minefield of potential interferences. The primary pre-analytical trap happens before the sample even reaches the lab. If a phlebotomist draws the blood too forcefully or leaves the tourniquet on too long, it induces mechanical hemolysis. Because red blood cells naturally sequester triple the selenium concentration of the surrounding plasma, those ruptured cells flood the sample. The analyzer will read a falsely elevated concentration, completely masking an underlying deficiency. To prevent this, clinical teams must draw the sample flawlessly into specialized, trace metal-free royal blue top tubes, often executing a strict discard volume just to flush out microscopic metal shards sheared from the needle itself. Once secured, the sample arrives at the analytical gold standard, the inductively coupled plasma mass spectrometer. This instrument vaporizes the blood inside an argon plasma torch, burning at roughly 8,000 Kelvin, sorting the raw atoms by their mass-to-charge ratio. But this process introduces a massive physics glitch. In this animation, you can see how the extreme heat of the torch occasionally forces two argon gas atoms, each with a mass of 40, to fuse together into a single argon dimer. That dimer has an atomic mass of exactly 80. As the mass detector graph spikes, it creates a fatal isobaric interference because mass 80 is perfectly identical to the most abundant natural isotope of selenium. To protect the data, the laboratory engineers a physical workaround called kinetic energy discrimination. The ion beam is routed through a chamber flooded with neutral helium gas. The bulky argon dimers repeatedly crash into the helium obstacles and shatter, while the smaller, denser selenium atoms slip through safely to be counted. By deploying a microscopic aerodynamic filter, The laboratory strips away the interference, finally proving the true elemental composition of the patient's blood. Armed with accurate data, the consultant pathologist can issue precise directives back to the clinical wards to optimize patient care. This brings us back to the clinical blind spot we started with. Patients undergoing prolonged intravenous nutrition are highly susceptible to the T4 to T3 trap. When a physician observes unexplainable muscle weakness alongside a normal T4 and a crushed T3, they must rule out a trace element deficiency before chasing a diagnosis of central hypothyroidism. Conversely, if the laboratory registers a toxic alert value above 400 micrograms per liter, the clinical team must immediately discontinue all exogenous sources and maximize renal clearance with aggressive intravenous hydration. The protocol carries an absolute warning. Traditional heavy metal chelation therapy must never be used for selenium toxicity. The chelating agents will bind to the selenium and form complex compounds that drastically accelerate renal damage and neurotoxicity. Maintaining strict diagnostic stewardship means reserving these highly complex trace element panels for specific scenarios, monitoring long-term TPN, screening occupational dust exposures, or evaluating atypical endemic cardiomyopathies, rather than investigating generalized, routine fatigue. Human structural stability, cardiovascular rhythm, and DNA replication are not autonomous. They are permanently tethered to the microscopic elemental composition of the Earth's crust.